Hello everyone and welcome back to Agronomy Decoded. I am Dr. Priyanka and today we are tackling a high yield topic for your competitive exams, that is the measurement of irrigation water. Let's decode this together. Before we measure anything, we need to understand exactly what we are measuring. Look at this slide. Are we measuring water at rest or water in motion? When water is stationary, like a reservoir or a flooded paddy field, we measure its volume. You will see units like acre foot, acre inch, or cubic meter. But in irrigation management, we usually need to know how much water is actively moving past a point to reach our crops. This is known as flow rate or discharge. For this, time is introduced. We use units like cusacks, which is cubic feet per second, or cubic, cubic meter per second. Today we are focusing on how to measure this moving water. Start with the velocity area method. The absolute simplest and cheapest field technique is the float method. Imagine you are in the field. You mark out a straight 50-meter section of a canal. You drop a piece of wood or an orange into the water and time how long it takes to travel that distance. Distance divided by time will give you your velocity. There are some exceptions. If the object is floating on the surface, which is the fastest moving part of the stream, frictions may slow down the water near the bottom and sides. To get the true average or mean velocity of the whole channel, we must multiply our surface velocity by a standard factor of 0.8. And remember, if the field channel is narrow, rocky, or full of weeds, you must reduce that 0.8 factor even further. Next is the velocity head rod. Think of this as a specialized, inexpensive measuring stick. If you place the rod parallel to the water flow, the water just slides by and you measure the normal depth. But if you turn the rod 90 degrees perpendicular to the flow, it blocks the water. The kinetic energy of the flowing water hits the flat wood and pushes upward and creating a tiny hump. By measuring the difference in height between the normal water level and that hump, can use lookup table to calculate the velocity. For your exam, you can memorize the working limit. The velocity head rod is only accurate if the water is moving between 1.5 and 10 feet per second. If it is lower than 1.5, the hump is simply too small to measure accurately. Let us move to direct discharge methods, which are much more accurate. First up, weirs. A weir is essentially a small dam with a notch cut into it for water to flow through. If you are managing a canal where the flow is steady, fairly uniform, you will install a rectangular or trapezoidal weir. If you look at its formula, the depth or head is raised to the power of 1.5. However, if you are measuring a wild mountain stream, that is trickle in May but a raging torrent in July, you must use a triangular or V-notch weir. Why? Because its formula uses an exponent of 2.5. The higher exponent makes it incredibly sensitive and highly accurate for wildly variable flows. What is the biggest drawback of any weir means? The raised wall traps silt and sand behind it, which spoils your measurement over time. So to solve the silt problems, we use flumes, especially the partial flume. Because the floor of the flume is relatively flat, silt washes right through. A flume works by squeezing the water through a converging inlet, a narrow throat, and a diverging outlet. If the water drops cleanly through the throat, this is called the free flow. It's easy to measure. You only need to read the water depth at one single point upstream, which we call HA. But in the real world, weeds go downstream. This blocks the water, causing it backflow and flood the throat section. This is called submerged flow. When a flume is submerged, reading HA, that is the converging point, is no longer enough. You must also take a reading in the throat called HB and apply a mathematical correction to find your true discharge. Let's look at orifices. An orifice is simply a shaped hole with a closed perimeter that water flows through. The standard coefficient you need to memorize for the sharp edged orifice is 0.62. Orifices works brilliant for measuring small discharge. Okay, that brings us to end of this today's session. We have covered everything from the simplicity of the float method to the complex submerged of partial flumes. Thank you so much for joining me today on Agronomy Decoded. Keep studying hard, stay focused, and I will see you in the next lecture.